So let's start. So sorry, first of all, that I have to talk via laptop to you, but at least it's live online, so it's no pre-recording, as you may know it from some conferences. And I'm happy for the possibility to give you some of our results on CFD, high fidelity simulations of wind turbine effects in complex terrain under atmospheric inflow. Before I do that, I would like to acknowledge my co-authors, which are some PhD candidates from my group in Stuttgart. We also have two colleagues from NREL. They provided a generic wind turbine geometry and structure. And we also have two colleagues from Hanover. They did some LAS-based simulations, precursor simulations for our CFD. On this slide, I have combined, let's say, the perfect world and the real world. So on the left side, you see some dedicated wind tunnel measurements on the wake evolution past the model turbine under controlled laminar uniform inflow. Very instructive. You can learn a lot of that. You can identify certain small scale effects. You can use it for validation. You can do highly resolved CFD and identify effects like these turbulent worms that are wrapped around the tip vortice and so on. On the other side, in the real world, we have a turbine installed in a site. We have an atmospheric inflow. We may have topography, orography, and of course that has a strong impact on the turbine and on the wake evolution. So we have the challenge to bridge the scales from the very large scales of the atmosphere down to the very small scales that at the end drive the aerodynamics and also acoustics. And we approach this multi-scale problem by using a hybrid CFD method, a hybrid runs LAS on the turbine side. And then we have a generation of atmospheric inflow by different means that I will show you on the next slide. So here are some of the features of our CFD code. It's code named Flower, are depicted, but I will not go into details. You will see some results later on. We use structural coupling. We can simulate complex orography. We have coupling to acoustics and things like that. So how to generate the atmospheric inflow for the detailed CFD? So we have first the option that we can prescribe some shear profile at the inlet and then impose synthetic turbulence by different means. We use PyCon, but also a manbox for turbulence generation, and we inject it into the flow field. That was used in the first example that I will give, which is on the impact of complex terrain, also of stratification on the evolution of a wake. An alternative is to do some precursor simulation that cover a very broad domain. And here we have two examples. One is a precursor calculation using a steady run space code that was provided by our colleagues from NREL. And I have one example with me that goes into some details of the origin of low frequency noise of a turbine in complex terrain. Another option is to do resolved, scale resolved simulations, LAS simulations. And here I have an example from the colleagues from Hanover. They develop and use the PALM code, the LAS code, and we couple that to our CFD. And I will give you one short example, if time permits, on the impact of wind changes on the loads of a turbine with controller. But let's start with a first example, which is on the impact of complex terrain on wake evolution. And here we considered one site in South Germany, and that is a site where that is a WindForS network, erects a test site consisting of two, let's say, smaller turbines and equipped with a lot of field measuring technique. You see mass masts, we have LiDAR, we have UAVs, and the MetMAS and LiDARs were already installed quite some time ago. So we have already some detailed experimental characterization of this test site. And we also put it into the computer. So we did some CFD with our Flower CFD code, and here that's just a comparison of some measured boundary profiles in the test site domain compared to our simulations and compared to some LiDAR results and some UAV results. You see some spread here in the measurements from the different techniques, but it at least shows more or less that we can calculate reasonably well the characteristics of the boundary layer profile. And that was just the first step. The next step was to put a virtual turbine into the computational domain, and you can see the computational domain here. You can see the turbine with the wake. You can see the turbulent atmospheric inflow, and you can see the topography, but you can also see that this site has a lot of forested areas at the hillside, which we also consider in our CFD simulations. And that's just one example. We did simulations of this terrain with a virtual turbine. The real turbine is not erected yet, but will be. And we added also some impact of stratification. Yeah, so the first row, the above row, shows the results of the wake evolution for some unstable condition. You see cross section of the wake 2D downstream of the turbine, 4D and 6D. And the lower row shows the results for stable conditions. And there are quite some differences. You can see, as probably expected, for unstable conditions, the wake earlier dissolves, and we see also some convection, some motion of the core of the wake in upward direction, which is not visible in the lower row. Now that's just an example that shows that in the computer, meanwhile, we can simulate the impact of a complex orography, including forested areas under atmospheric inflow, considering stratification, and do some studies on details of the wake evolution. And I think Stefan and Martin. Second example that I would like to show is on some low frequency noise emission. And on this slide, I depicted, let's say, the main source, the origin of this low frequency noise on the example of the NREL turbine, flexible turbine. And you can see for the rated condition shown here, we have a strong bending, and the blade to the tower clearance is quite small. Now, so that means every time when the blade passes the tower, it impacts the flow field around the tower significantly. You can see the velocity field here, and you can see the pressure field here. So we have a very unsteady pressure fluctuation imposed on the tower. And unsteady pressures mean noise emission. And the tower, unfortunately, has a very large surface, so we have a huge emitter of this low frequency noise. But the impact is also vice versa. Of course, when the blade passes, also the tower displacement imposes unsteady pressures on the blade. And that's also a second emitter of low frequency noise. And here we will see that atmospheric inflow has quite some impact on the two contributions of the low frequency noise. We did this calculation for a generic turbine. It's denoted I82 that was provided by the colleagues from Enercon. And that generic turbine more or less mimics the macro data of the real E82 turbine, but with public domain airfoil series, with some differences in the blade design, in the structural design, and also in the controller. But it's a very good example of a 2 megawatt turbine for these kind of studies. And you can see we jointly set up the mesh, 17 components. We have overlapping meshes for the different components and end up in the order of about 50 million grid cells for this turbine. We also set up a structural model in SIMPAC, but I will not go into details of this. We did this example for the well-known Perdigão site, which shows these characteristic two ridges here. And there is one real E82 turbine on the first ridge. And on that position, we also put our virtual I-82 in the computational domain. And you can see the CFD domain, the flower domain here. In this case, a quite big domain. So we have dimensions in the order of 4 to 6 to 4 kilometers. We have a very fine resolution in the domain of interest, in the inflow of the turbine, but also around the turbine in the wake. We have a resolution in the order of 1 meter, and that unfortunately provides some 240 million grid cells plus the grid cells from the turbine. In this example, we did a coupling with the so-called EERA code by Enercon that they use for site assessment, and that's a steady state runs code. So it only provides steady state boundary layer profiles, but no resolved turbulence. They cover a huge domain, and they adjust the inflow profiles of the computational domain in order to mimic some measured profile near the turbine. And they provided their results, and we fed them into the flower CFD calculation in this red inflow plane shown here. So here you see some results of the flower CFD calculations. As mentioned, we impose the steady state boundary layer profiles. In order to generate the required turbulence, we just take the statistical turbulence properties from EERA, transferred that into turbulence intensity and length scale, and fed that into a MAN box. So we have a synthetic turbulence generation that somehow mimics what has been calculated in the precursor simulation. This is just to show you that we did a full structural coupling for C simulation. You see the turbulent atmospheric inflow, you see the orography, and not surprisingly, we have a very strong impact of the turbulence and the terrain on the deformation of the plate. Here you can see the tip deflection shown in blue compared to the predicted tip deflection for uniform inflow and flat terrain. So a strong impact, and of course that also shows in the next evaluation, which is the surface pressures on the tower but also on the plate, in order to derive information about the low frequency noise emission. On the left side we have the results for the uniform inflow, flat terrain. On the right, the turbulent inflow, atmospheric inflow for the Perdigão terrain. And we have in vertical direction plotted the frequency in terms of multiples of the plate passing frequency. And on the horizontal axis, we have the azimuth angle around the tower. And the evaluation is done for this height of 50 meters, which is marked here by this red line. Now, what we can see clearly is that we have a very strong signal, a very strong pressure peak at plate passing frequency and the higher harmonics. We see that for the uniform inflow, but we see that also for the turbulent inflow. Yeah, there are slight differences. So turbulence obviously reduces a little bit the amplitude, smears a little bit, but it's not very significant difference. So the main impact is the tower passage. But we can indeed see some difference. If you look on the left side, we can see a very strong peak, a very strong signal in the rearward side and the sides of the tower. This is at 0.6 Hertz. And if you transfer that into a Strual number, it's 0.19. And that is what we expect for the vortex shedding frequency of a cylinder. And actually, if we look into the flow domain, we see that we have a very coherent detachment of these cyclic vortex sheets, which is just in line with the theory. So that's a very strong peak here. If you go to the right side with a turbulent inflow in the terrain, we see a much weaker signal. The amplitude is much smaller. And if you look into the flow field, the coherence of the vortex shedding indeed is dissolved. So there is not a unique frequency. There are a number of frequency weaker vortex sheets that are detaching and that smears a lot the signal, but it also reduces the amplitude. So you can see turbulence, atmospheric turbulence has a significant impact on the contributions of the low frequency noise. Now, next slide is on the results on the turbine plate. Here we have depicted on the horizontal axis the distance from the leading edge, in vertical direction, again frequency, and we can see for both uniform and turbulent, we can see strong signals at the rotor frequency and higher harmonics. But this time you see turbulence increases the amplitude, increases significantly the amplitude for the signal emitted from the plate. You see the amplitude is higher. We see only red colors. We see a smearing. We see a more broadband response. And that was quite interesting because turbulence, atmospheric turbulence, changes the situation for the low frequency noise emission significantly. When we look into uniform inflow, we can show that the tower is the main emitter. When we look into this situation, this turbulent inflow, we could see that actually the rotor is the dominant emitter, and the rotor has a different directivity of the noise emission. So that changes the characteristics, and you see if you apply these highly resolved simulations, including atmospheric inflow and including a highly resolved CFD for the turbine, you can study the impact of turbulence of a certain site on the mechanism of the low frequency noise, and you can identify the reason for certain directivity characteristics. And now let's come to the last example, a short example, that is on the impact of wind direction and wind speed changes on the turbine with a controller. So in the computer model, we added a computer, a power controller, pitch controller, and a yaw controller, which are activated during the CFD simulation. And this time we used a scale-resolved precursor simulation with an LES code. In this case, it's Palm, developed by our colleagues in Hanover. And then they have a nice feature. They have a nudging approach. That means they can impose a source term in the simulation in order to urge the simulation to follow a certain time signal of the wind field. That can be seen here on the left side for the wind speed. So measurement that where the target distribution is a blue curve, and what was realized with this LES simulation is a red one. It's not identical, of course, but at least you can see the same trends: wind speed increase, decrease. The same holds for the wind direction. Here we see a clear trend in a change of the wind direction, also in the simulation. And this signal was then imposed to Flower, and this time we do not need any synthetic turbulence because it's included in the LES. You can see here the LES domain provided by Palm, and then you can see the propagation in the Flower domain. We start usually with some simulation time without virtual turbine, so to propagate the turbulence through the CFD domain. Then we add the turbine, but first a few revolutions with a rigid turbine. Then we add flexibility, and then lastly we add also the controller signals. And that brings me to the last technical slide. That are some results of the simulation. On the left side you can see all the control commands which are exactly realized in the CFD simulation. So in the CFD solver follows the yaw commands given in green here. The CFD pitches according to the pitch controller, the blue line, and also the RPM is adjusted according to the controller commands. And that provides at the end forces seen here on the right side for the axial force, but also for the moment. And you may observe we have some oscillations here in the pitch controller, and that just stems from the fact that we have some yaw misalignment here. So we have chosen a situation where we have a constant change in wind direction. The yaw controller is slow, so here we see some yaw misalignment, and that activates the pitch controller to some extent. So that concludes, in principle, my presentation. I tried to show you that meanwhile, with the CFD tools we have, we can simulate all effects at a turbine. We can consider flexibility, we can consider controller, we can do acoustic calculations, and we can also account for atmospheric turbulent inflow. And that's quite useful tool for us at university. We can study detailed interaction effects, interaction atmospheric inflow with a turbine, impact on noise emission, noise mechanisms, but also loads and things like that. But also for industry, our industry partner also uses CFD. They verify the turbine designs and they do some kind, they call it forensic investigations. So they switch on the CFD with some atmospheric inflow if they observe in the field some unexpected behavior at a certain site of a certain turbine in a certain wind condition. So it's also useful CFD for industry. That concludes my presentation, and thank you for listening to me.
Thank you very much, Thorsten. Do we have any questions in the audience here or questions virtually? Remember, please type in your question if you're joining us virtually online. I have a question. So I was very interested in the slides you showed there with looking at the difference between the noise emissions from the blades and from the blade or from the tower, depending on whether you're doing the turbulent flow or the more from the flat terrain situation. We've heard these last days also about the need for more onshore wind, and I'm wondering whether any of these findings can move us in a direction for mitigating noise emission, or at least better understanding it and planning kind of out of it. Do you have any response to that?
That's our goal, yeah. So in this respect, I have some kind of a mission. I know it's a very delicate topic, so infrasound and low frequency noise, but let's say it's a consequence of the technique. The blade passes the tower, so we have this kind of signal. Yeah? And we are in the position now to simulate it and to understand it. Yeah? I mentioned the different directivity. For example, if we have a high turbulence, the rotor emits, and the rotor emits more in wake direction. If we have a low turbulence, tower is dominant, emits in all directions. Yeah, so it explains, or it may help to explain why people are annoyed by certain turbines under certain conditions. And as mentioned, my mission is to keep on working on this topic. It's not liked by the industry. It's sometimes ignored by the industry. But at university, we can provide some explanations on effects. And at the end, also look for mitigation techniques. And I think there are some chances, if you realize that the noise stems from this interaction, you can think about some countermeasures, of course.
Thank you. Thank you. And there's another question from the online audience, saying, it's from Catherine Meissner, saying, nice talk. Could you say something about what kind of controller you used? Is it freely accessible?
That was a controller. It was on the slide. It was a bit fast, but it was based on some public domain controller. There were 3 controllers mixed, and that was done by our colleagues from NREL. So this controller is not actually public domain, but it's also no commercial controller. It's based on a controller of NREL turbine, and so it's half public domain. Yeah. If you are interested, I can contact the colleagues. Whether they would be willing to provide. Yeah.
Thank you very much, Thorsten. And we've actually run out of questions, run out of time, but we haven't run out of questions. So, Thorsten, if you were able to, at some point, look at the chat, there are some more comments and questions there coming in. So, yeah, thanks very much to the online audience for coming up with more questions.